So we are Cornell Hyperloop. My name is Mark Edwards. I am a sophomore studying mechanical engineering, and my colleague today is Nikita Dogopov, who is also a sophomore in mechanical engineering. And we have been making this stability and guidance system for the past few weeks and the past month under the supervision of our sub-team leads, Jack Crespo and Mahika Goyle. So Cornell Hyperloop was originally established in 2017. This will be our first year competing competition. So this year in 2020 begins a 2-year cycle of first tackling, magnetic levitation, and propulsion.
Yeah. First, I want to start with the requirements that we have for our system. We want our guidance and stability system to provide stability in lateral, row, and yaw directions. You can see them marked on the diagram on the left with like red arrows. Yaw is the spin about the y-axis, lateral is the long red axis, that is the x direction, and our pod will be moving in the z direction, with roll being the spin about the corresponding axis. The main purpose of our system is to bring the pod into the equilibrium position in the case of any external force that affects it, and we want the system to do it safely and quickly without entering any no-entry zones and not touching the track by itself. So the geometry of our system is mostly based on the I-beam configuration that is 5 inch by 5 inch, and the usable space inside the I-beam where we can where the roller of our system can touch the I-beam is only about 2.5, 2.7 inches. So that's also considered in the design. Additional consideration is the design of our chassis from last year's, to which the guidance system will be attached. Its width is 12 inches, as you can see on the diagram on the right. And as for the forces that are acting on the system, we expect that the gravitational force will be counteracted with the levitation force. And the levitation height we expect to be at minimum 3 millimeters. A regular value for it would be about 5-6 millimeters. So 3 millimeters is our critical case, and it will be used in the future calculation that we will show in one of the future slides. So that's the main essentially forces in the y direction. And as for the x direction of that is the lateral direction of for our pod, we only expect the spring forces to act in that direction. And we expect them to be approximately horizontal because of the small angle approximation that we will be using. So roll and lateral stability will be fully controlled by the forces exerted by the springs.
So the system we decided to use is a mass spring system, which can be seen on the right-hand side. This is our explode assembly view from SolidWorks. And kind of going left to right on our system, the left-hand side is the arm, which will be attached to our chassis and will be bolted in with the top 2 cuts. And then from there, the backside of this arm will be bolted to this kind of larger base plate. And from there, we have a stability rod in the middle of our system. This rod will be inserted inside the inner hole of our base plate. And then from there, we have a pin inserted in through that hole, which will kind of keep our stability rod in place while also allowing for some kind of translational degree of freedom given that inner cut it out slot. And then from there, the right-hand side of our stability rod will be threaded into this other right-hand plate, which will then be bolted to this ball bearing. And the actual spring will be wrapped around the stability rod and can freely kind of compress and expand kind of due to that translational degree of freedom. And the right-hand side is our Hudson bearing. We chose a Hudson bearing because it allows for our pod to still be in contact with the I-beam given any kind of tilt angle compared to just a traditional wheel with just one axis. So how the system will actually work is given our I-beam will have some kind of initial compression. So our system will actually be in contact with the I-beam at all times and will initially be compressed, and then given some kind of tilt angle or some lateral stability, we will then further compress our spring and then kind of restore back to equilibrium. As far as actually manufacturing this design, Nikita will further touch on that.
Yeah, so Mark already explained the assembly of the system, and as for the manufacturing and the purchase of the components, we are going to purchase a ball bearing. That's the ball bearing we are using in our design is a regular transfer ball bearings that would be used in a factory to transfer parts, and we are currently implementing it, and a bit on its performance we'll talk in the future slides. Additionally, we are going to purchase the spring The current spring dimensions are about 1.5 inches long, 1 inch wide. The spring constant is around 150 pounds per inch. So that's the spring we are going to purchase at this point. The manufacturing of the system, so everything else in the system will be manufactured in the Cornell machine shop, and we already passed this, training for it and obtained our certifications. So we are soon going to start manufacturing the other pieces.
And then as far as just future design considerations, we will be looking into using some kind of damper or shock absorber rather just like a regular spring because of kind of potential oscillations due to us compressing and then kind of expanding that spring back to equilibrium. So that will be touched on in further slides.
Yeah. The following slide presents you a cross-section view of the system on the left. As you can see, the L arm is about 6 inches tall, and it's about 5.8 inches long. That gives us very small pre-compression in each spring on each side. The system is also about 2 inches tall and 2 inches wide. That's one area where we can really cut a lot of weight on the system, and it's also one of the steps we are taking right now. As you can see, there is also there is not much space on the I-beam, only about 2.5 inches between the no entry zones where we can place our system. And currently it satisfies this requirement because it's still smaller than 2.5 inches, and it also has some room for displacement in the Y or vertical direction in case of any force instability. And on the right, you can see the diagram for the placement of our guidance system. As you can see, there are two pairs, one at the back and one at the front. That's made to prevent any instability in the yaw direction that is around the vertical Y-axis.
So in looking at possible design options and choices, we had three main things in mind. The first system was some kind of magnetically controlled levitation system that would utilize electromagnets, as can be seen on the diagram on the right-hand side. So we'd have some kind of electromagnet on both the right and left-hand side of the system, which would provide a lot of control. But the main issue with this, the reason we decided to choose it, was simply because between having a linear induction motor, having hollow block arrays in our braking system, and then also including these pairs of further electromagnets, we figured that would potentially cause too much interference and wouldn't really make sense as far as ease of integration with the rest of our system. So we decided against that. And then our initial other idea was some kind of linear actuator spring system. So this would be very similar to our current passive spring system. Just the main difference would be instead of having some kind of damping, we would have a linear actuator that would both extract and contract, which would then basically bring our stability system either into the I-beam or away from it based on kind of how our pod is moving and tilting. And just the main issue with this and kind of our main design constraint is simply based on the size constraint of kind of only working with about 6 inches between where we're actually coming off our chassis and then kind of touching the I-beam. So between having some kind of Hudson bearing, some kind of spring, stability rod, a base, an L-arm, all of that, plus a linear actuator, we just figured there wasn't simply enough room to do all of that. So that's kind of the main reason against this system. So that kind of left us with our passive spring system, which implements both a ball bearing, a spring, and then kind of our L-arm. And as far as the design trade-off study of that, Nikita will touch on that.
Yeah, so here's the trade study that we've conducted, and here we are comparing the systems that we mentioned in the previous slides. As you can see, to each of our properties of the system, we assign a weight, a corresponding weight, such as complexity has a weight of 0.2, size and weight has a weight of 0.3, and additional criteria for our systems are the ease of integration of it into our current pod design and with our other systems, the economic cost of it, that's how expensive it will be to produce, to purchase the components, and finally the benefit of each system. That is, for example, magnetic system can provide us a lot of control over the lateral and roll stability, but for example, ball bearing spring system is a passive system, so it's not as so it would not bring as much benefit on the large scale. So the numbers in this table, in the category 3 means that current item is the best in this category, while 1 assigned to an item means that it's the worst in this category. So as you can see, the ball bearing spring system and wheel spring system are the least complex. They have smaller size, they have smaller weight than magnetic or active spring linear actuator systems. In addition, they are much easier to integrate into our pod design. So, of course, they came out on top in our table with the scores of 2.4 for wheel spring system and 2.7 for the ball bearing spring system. The only difference being that ball bearing can provide more freedom in motion for the system in case of vertical displacement of it. For example, a wheel may actually just scratch the I-beam since a wheel can only move along one axis of motion. So that's why we chose the ball bearing spring system for our pod. Yeah. So for designing our system, we used a kinematics approach, being the easiest to implement for the preliminary design and just estimating the properties that our system will have. In the future, we're actually using to also implement the dynamics approach to verify our calculations or potentially obtain any new results that can change the current design. The first thing we did when designing the system is we made a following diagram on the left with Cm denoting the center of mass of our system, with point B and A denoting the points of spring forces applications, and using the distance from the center of mass to those points of spring forces application. We can actually calculate the displacement in each spring given the angle of roll theta. So you can see the equation just under the diagram.
So when first using a kinematics approach and using angular equations of motion, we had to find a way to model the total moment of inertia of our pod, which was kind of pretty confusing at first, given both an aeroshell, some kind of chassis system, and then all of the moving parts within it. So we decided to initially use SolidWorks and its mass properties to get an idea of what the center of mass and the moment of inertia of just the aeroshell would be using the plugged in mass properties. And then from there, we treated the actual chassis with all of its weight components as just a mass concentrated prism, which from there gave us a moment of inertia for both the aeroshell and that prism. And then kind of using the parallel axis theorem, we combined it to model the total moment of inertia of our pod. And then given that, we had the following equation for our spring constant K, which can be seen at the bottom here. And knowing this equation, we could then base our angular acceleration off of some kind of plugged in time constant, which gives us the following graph right here. And our time basically varies. So our equations are time dependent. So based on our plugged in value of time, we kind of get a spring constant in return. So varying our time from roughly half a second all the way to 2 seconds gives us the following spring rates in pounds per inch. So roughly between 450 down to 25 pounds per inch is our suspected compression rate. And then from there, we figured based on our system and kind of how fast we want to return to equilibrium, it would make most sense to have a return time of roughly 0.75 to 1 seconds, which gives us basically a spring rate of 150 pounds per inch. So when actually looking for specific springs, shock absorbers, dampers, we often use this value to kind of see how realistic it was to implement this spring compression rate given the tight size constraints of our system.
Yeah, so as for the future steps that we are going to take, we want to verify the performance of ball bearings under high speeds, as I mentioned earlier. We are not exactly sure how they will perform, and so the testing has to be done to make sure that the system would not fail under the high speeds that we may encounter. Furthermore, we are working on reducing the thickness of our L-arm for our guidance system. We are additionally running fusion generative designs to potentially get some new shapes and ways of optimizing the mass of the system given a factor of safety of about 2.53. Yeah, and additionally, we're running the ANSYS simulation, and Mark will cover it a bit better right now.
Yeah, so the right-hand side diagram kind of gives our ANSYS simulation with our factor of safety. So when actually kind of modeling the system using ANSYS, we decided to kind of looking at the right-hand side of our system, we have this outer diameter and then an inner cut. So the outer diameter is basically where our spring will be placed and kind of compressing against this L-arm. So we decided to kind of model this compression and this force as a pressure force. And we decided based on roughly 150 pounds per inch of compression, we would have about 360,000 pascals worth of pressure. So we used this value and actually running ANSYS, and that gave us a very high factor of safety for the majority of our system of roughly 15, with our minimum factor of safety coming around this second hole, which will be kind of bolted to the chassis of 4.0. So given these high factors of safety, we can definitely further reduce the size of the system to kind of make it more efficient based on just simply a cost and weight reduction analysis. And then from there, we also plan on looking into further using dynamics approaches to kind of not eliminate, but kind of reduce the time dependence that our system currently has. So when using kinematics, we kind of decided to use this approach just because it gives us a good idea of how to initially model our system and then kind of see what can be changed and kind of fixed from there. And then further, we also plan on definitely looking further into shock absorbers and dampers to make sure our system doesn't have any kind of further oscillations when we kind of come back to stability. So these are our future approaches, kind of how to fix our system before a final design review. And then after that, next semester, we plan on manufacturing it. But that is kind of the overview of our system and what it tends to do. So I will now open the floor to any questions that you guys might have.
That was a great presentation, guys. Quite a wholesome presentation, right from your requirements to actually what your design and future scopes are. Now the floor is open for any questions. So feel free to either switch on your video and your mic and ask your question, or you can type it in the chat box and I can facilitate asking the question. Yeah, we have Sanchit Devadkar asking a question. Please go ahead.
So my question is that did you all while designing, did you all do a motion study of the?
I'm sorry, Sanchit, your voice is not that clear.
Is it clear now?
Yeah, much better. Please go ahead.
Yeah. So I would repeat. My question is that while designing, did you all consider doing a motion study or anything of that sort? Because seeing from the design, there's a chance that the design might act as a cantilever and then your wheel might just move up and down while having a contact with the web of the track.
Sure, that's a good question. Do you want to touch on that, Nikita?
Yeah, it would be just better if you a bit rephrase the question, because I didn't fully get it.
Yeah, so my question is, while designing, did you all do a motion study or a motion analysis of your design while applying the constraints? Because seeing at the design, I have a doubt that it might act as a cantilever and your wheel may just go up and down constantly throughout the run.
Oh, yeah, I see. Yeah, so as Mark has mentioned, in the case of so one of the future steps for our system is introducing a damper instead of the spring, which would actually allow us to reduce the oscillations and prevent them from staying there permanently. As for the displacement in the y direction, I believe the question was about this. I believe there will be oscillations independent really of the system. But fortunately, the room that we pick for our system, that's about 2.5 inches, and our system is about 2 inches tall, right below the I-beam, I mean, in the middle of it. We believe that this room should be enough for the system to operate without entering any no-entry zones. So we don't expect to see any issues there.
Yeah, we also made sure to choose the Hudson bearing simply because if we were to use just a normal wheel that was touching the I-beam, given some kind of tilting angle, we basically lose contact with that wheel and the I-beam. So that's kind of why we chose the Hudson bearing with its kind of ball-shaped design, so that given we're tilting, we're still in contact with the I-beam. And we decided to be in contact with the I-beam simply due to the fact that we'll probably use some kind of chrome steel Hudson bearing, which will have very small to negligible friction with the I-beam, and we've decided it would be best to be in contact with the I-beam rather than kind of slightly off it and then potentially kind of produce some kind of moment or further tilt if we then were to actually touch our stability system. So although we are in contact with the I-beam at all times, we don't suspect that it'll kind of cause much of an issue.